In this session, we're going to take a look inside S19 files. An S19 file is the executable code that is produced by a Freescale or Motorola-based processor when you write assembler code. So if we look at this code here, for example, we can see we've got some variables defined here, we've got some constants, we have our code down here. So we can see we're loading X immediate addressing mode with the address of an array, or the starting location of an array. We're loading A with a number, which is defined up here to be 26. We're loading B with the contents of value 1, which we don't know what's in there right now, but it is a variable. We're adding A to B. We're storing the result in the array. We're moving to the next array element, and we're then comparing to see if we're at the end of our array. If we're not, we're going to go back, loop back, and do some more arithmetic. Once we finally get to the last element of the array, we've got from the beginning to the size, which is defined as 5 elements. Once we've dealt with all 5 elements, we won't branch anymore, and we'll come down to the end of our program. So we've written our code. We would then run it through the assembler to generate both a list file and our S19 file. So here we can see the output of the list file. We can see our constants defined up here. So there are the hexadecimal values that 26 and 5 represent. Here we can see our variables. They're declared in RAM, so remember RAM is where we can read and write from, and they're at addresses 800 for the first one and 801 for the second one. So value is stored at address 800. Array, which has a size of 5, starts at address 800, so it's going to be 801, 802, 3, 4, and 5. Now our code is down at the bottom, so we can see here two things. This column has the addresses, so we know that our code goes in ROM, so this is not changeable, starts at address 4000 and goes right through to 4010, 11. So our last byte of our code would be at address 4011. The first instruction takes 3 bytes, CE, 08, 01. So that's the machine code in this column that's associated with each of the instructions that we have over here. So if we want to look at the add B to A instruction, for example, we'd come over and we can see the machine code for that is 1806, and it is at address 4008. So all of the information for each instruction we have over here is provided to us in that list file. So the list file is very, very useful to you. Make sure that when you're working with assembler code, you're always working from your list file. More important as far as the processor itself is concerned is the S19 file, and this is also called the object file. So it's called an S19 file because it has a .s19 extension. It's a text file. If we open it up in any text editor, this is what we're going to see. We can see that each line in the file starts with an S, hence the S in the file name. Then we have an S0 lines, we have S1 lines, we have S9 lines. So that's why the S19. I guess they decided not to put the 0 in. Then we have a lot of hexadecimal bytes per line, and we're going to look at exactly what those mean in a minute, but let's point out a few things here. Our code starts at address 4000, and if we look in the last S1 line, we'll see FFFE, and that is our reset vector. And that reset vector is responsible for telling the system where the code that it's supposed to execute starts. So if we look at what follows that, we see 4000. And that 4000 just happens to be the starting address of our code. So our reset vector tells the processor to go to address 4000 and start executing the code that it finds there. Now, you will also, in your S19 file, see that 4000 as a starting address here. So we saw address FFFE. Here, we're seeing address 4000. And if we look at what follows that, CE08018618A F6. CE08018618A F6. And if you follow the rest of that line, you will see all the bytes that correspond to the machine code for your program. So let's take a closer look at what's inside. There are 5 main parts. There's a line type, the number of bytes, the address, the actual machine code, and a checksum, which is used because this data is being transmitted from one platform to another platform, and this is a way just to make sure that what's being transmitted is actually received properly. So let's start with line types. The first 2 digits are always going to represent the line type. So we're going to see S1, S0, or S9. The ones that we're most concerned with are the S1 lines because that's where we're going to get the information we need for our machine code and our reset vector. The second bit of information is the number of bytes. So the next 2 characters represent the number of hexadecimal bytes that are going to follow on each line. So if we look at the last line first because it's short, it tells us that there are 3 bytes. So remember, each hexadecimal digit represents half a byte or a nibble. So 2 digits make a byte. So our first byte is 00, our second byte is 00, our third byte is FC. If we look at this line, counting in hexadecimal, each two characters represent 1 hex value. So BF is our first, FE is our second, 80 is our third, 00 is our fourth, and BD is our fifth. And we can do the same thing up here, 12. Remember, that's a hex value, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F, 10, 11, 12. The next piece of information is an address. So here we can see an address of 8000, an address of BFFE, and an address of 0. So you remember from the last time that the last S1 line has our reset vector. So here our reset vector isn't BFFE, isn't FFFE, which it usually is, it's BFFE. If the reset vector is going to be anywhere other than FFFE, a processor may put it at BFFE, and that's usually to allow for an expansion on the board. So here our reset vector is at 8000, which is where our code starts. So we can see that 8000 address here. Now, the next piece of information is the machine code. And that's what's going to follow. And that is this section right through here, not including the 3. That was kind of an overflow there. So my code here is CC001F, C30000, and so on. So the machine code is always going to specify the actual instructions need to be executed. Now in the next line, the 8000 falls into that same category, but here it's actually pointing us to our code. The last one, our checksum, is the last 2 digits on each line, and what happens is there's an arithmetic process done on each of the values in a line, and that generates that 31, that checksum. When the file is received at the platform that's going to actually run the program, it does the same arithmetic to make sure that when it does that same process, it gets a 31 there. If it doesn't get a 31, it means maybe there was a problem in transmitting. So maybe this DD didn't come down as DD, it came down as DB. or something like that. That simple way of checking ensures the integrity of our data. So we have line types, we have number of bytes per line, we have addresses, we have machine code, and then finally a method of validating the transmission of our data